recording.
Okay.
All right. Okay. 7E, describe the composition of the sun, its relationship to other stars, and some effects of the radiation on Earth's weather and communications. The sun is a giant ball of almost entirely hydrogen gas. The Big Bang formed the element hydrogen, which is one proton, one neutron, and one electron, the simplest element. And all the elements after that, the Big Bang made a little bit of helium, which is 2 protons and 2 electrons. And those are the 2 simplest elements, the first 2 on the periodic chart. All the rest of the elements were formed in stars fusing hydrogen and helium together into other elements. So when a big cloud of hydrogen is floating around after the Big Bang, it starts to be pulled together by gravity. As it's pulled together, there's more gravity and it collapses into a star. When the gravity is of sufficient force, it then squishes the hydrogen into such a highly concentrated mass that it essentially starts burning the hydrogen. That is to say, fusing it. And by fusing 2 hydrogen atoms, you basically slam them together, they form a helium, and they give off energy. And they burn the hydrogen and form helium. And that is the process by which solar radiation is created. And that's the sun's radiation and all the stars' radiation, right? So a sun is a ball of gas in various layers. It gives off radiation from the energy of the fusion in its core. And it rotates around and has convection and has weather and sunspots and flares and stuff like that. So the composition of the sun is hydrogen in layers. The relationship to other stars, some stars are smaller and older than the sun and kind of burnt out. Some stars are younger and much larger, from stars like Vega, which is much larger than the sun and burning up hydrogen at a high rate. Eventually, like the sun, it'll turn into a red giant and cool off and they start expanding. The sun is a middle-aged star. It's not a young star. It's not an old star. It's right in the middle of the sequence, basically. The effect on Earth's weather is almost all of our weather, the clouds, the winds, the convection of evaporation and the heat that is formed on the Earth, almost all of that comes from the sun. So you could say Earth's weather comes from the sun. That's just how that works. If it weren't for the convection of currents of the sea and the air, we wouldn't really have the rain and the wind and all that. The effect on communications, solar radiation slams into the Earth. A lot of it is deflected by the magnetic sphere around the Earth, but some of it comes through, and we hear that if you turn on a radio and tune it to a part of the dial that doesn't have a radio station on it, you hear static. That is mostly the sun emitting radiation in a random pattern, and that's what static is. You could also see it if you had an old style TV that wasn't cable and you turned it to a channel that wasn't broadcasting, you'd see all this white fuzzy stuff on the screen. That is radiation from the sun. And when big flares and coronal mass ejections happen, big fluxes of energetic particles come from the sun, and they can actually knock radio and cell phone and TV communications out.
It's okay, just getting started now.
Sunspots are twisted up magnetic storms on the surface of the sun. So the definition of a sunspot is a magnetic storm. And its effects are that when there are a lot of sunspots, we get more solar radiation and we can get those flares and coronal mass ejections. So it can actually affect satellites, communications, digital technologies. It can even induce currents in power lines and telephone wires. So sunspots and sun activity can have an effect here on Earth. 7C, that's it for the slides. So let me just do 7C. 7C, a red star you saw tonight is going to be Antares. And that is a red giant. Red means cooler. A blue star, Vega, directly overhead. White, tinging towards blue in the case of Vega, is a younger star and it means hotter. A yellow star like the sun could be like Alpha Centauri, if you want to put that. That's going to be a middle-aged, or if you want to call it normal sun-like star. And stars have a lifetime. They start out at a certain size and they change. Really big stars can crush. Crush is not a great word, but the force of gravity causes fusion. And if a star is big enough or blows up in certain ways, it can actually fuse helium into lithium and carbon and these other atomic elements. In the really, really big explosions and stuff, it actually forms metals. And all of the metals in our bodies, all these elements, were fused in the center of a sun and blown out into space and eventually formed part of our solar system and ended up on Earth and ended up being part of our bodies and our cars and our glasses and our computers. So all that stuff is forged in stars and explosions related to stars. And only something with massive, massive force, particularly gravity, has enough power to induce that kind of fusion. Even just fusing hydrogen into helium, which seemed like that would be a really good power source for us to run our power grid off of, we haven't actually yet been able to figure out the engineering of sufficient force to push the hydrogens together with enough force. And they're working on it. When I was your age, fusion power was supposed to be 20 years away. And the most recent report is it's still about 20 years away. So maybe one of you young guys will figure it out and find us a clean source of energy in fusion as opposed to burning fossil fuels or other forms of energy. So the meaning of the colors, just to finish 7C, is going to be red is cooler. It's still really, really hot, but it's relatively cooler. And white to blue tends to be much hotter. And then yellow is going to be in the middle like our sun. So that is going to complete all the requirements through 7. For number 8, we're doing the Star Party one. So that just wrote down whatever you see tonight. And then number 9, we're going to do with our astronomer, Spencer Suhu, who's going to be sharing his telescope and some views with us of what we're looking at. So you guys can relax, work on your worksheet, and then we'll have a question and answer session after our viewing. And we're going to do a little career panel with Tim. The guy that looks like Gandalf there is Tim Thompson, our astrophysicist guest. Thank you for joining, Tim. I think that background is Mount Wilson, which we saw a picture of the 60-inch earlier.
That's it. That's Mount Wilson.
Yeah, right above Pasadena, a very famous observatory here in Southern California. So Spencer, if you're ready, I'm going to go on mute and let you sort of give an introduction and show us what we can see in the sky tonight.
Okay, let's see. Can you guys hear me?
I can.
Yeah.
Okay, fine. All right. Okay, great. So unfortunately, it's kind of, the clouds are moving in, so we're not going to get a chance to see a lot tonight. But let me share my screen. So we should have done this earlier when it's still light, but have a telescope set up with a camera hooked up on the back of it. It's a Schmidt-Cassegrain, and Greg mentioned that earlier today. So it's one of those hybrid telescopes, and I've got an SLR camera hooked up on the back end, and that's going into a USB port on my computer. And so I'm going to share the screen. So I'm zoomed in on Jupiter right now.
Oh, that's great. It's a good view.
Yeah. So you can see 4 of its. Go ahead.
Yeah, go ahead and explain to the scouts what they're looking at. I know it's coming through your telescope and camera, but what are we looking at?
All right, so you see Jupiter, which is that huge ball right there. And then you can see one of its moons right there in that magnifying glass. See one of its moons, that's Callisto. And then moving down, it's Europa, Io, and then Ganymede right near the bottom. So just again to zoom in. So now over the course of the evening, those moons will change position as they rotate or they orbit around Jupiter. Now, I was playing around. Unfortunately, it's one of these things where you're sort of stuck, because if you want enough power, enough brightness to see the moons, enough amplification to see the moons, it washes out the color. And unfortunately, I was trying to play around with trying to tone down on the brightness so that you could actually see the colors in Jupiter. But this is my old camera broke, and this is a new one, and so I've been futzing around trying to get it to control the gain. So unfortunately, I can't do that. But normally you'd be able to see colored bands around Jupiter, like like the pictures that you've seen in the from NASA, JPL. So that's Jupiter, and one of the cool things, if you're into it, is you can actually watch the shadows of the moon as they cross the surface of Jupiter. And the other thing is, if you're actually looking at it now, unfortunately, looking at it through a telescope, to the camera, to the computer, you lose a lot. So in my opinion, there's nothing that beats looking at an object like Jupiter with your naked eye, with your eyes, with your own eyes, not going through the electronics. All right, now as we mentioned, Saturn is a little bit to the left of Jupiter, so we'll swing over to Saturn and see what we have there.
Yeah, so I think for the scouts, Jupiter and Saturn, which most of the scouts were able to see tonight when they went outside, they're over on the eastern horizon. And, when things are closer to the horizon, that means you're looking through more atmosphere than if it were directly overhead. You can often see more directly overhead than you can near the horizon. There tends to be a bit more pollution near the horizon, more cloudy, dusty stuff. And some of that, like Jupiter, looked like it was kind of moving left and right. That's not the planet Jupiter moving. That's probably the atmosphere and some of that dust and stuff kind of obscuring and causing some false motion. Oh, there we go.
Okay. All right, Saturn. So you can clearly make out the rings.
That's a beautiful view. Thank you, Spencer. This is live through a telescope, right?
Right. So again, it's still kind of low on the horizon, and my telescope's not really that well aligned, so it's drifting. This is where Greg mentioned that the Earth's rotating, and if your telescope is not directly, perfectly lined up with the axis of the Earth, things do tend to drift. Let me just get this back in and zoom in just a little bit.
So as I mentioned earlier, the first astronomer to see the moons of Jupiter and the rings of Saturn was the guy who invented telescopes, and the first one to look through them, the refracting telescope by Galileo. And by looking at the rings of Saturn and the moons of Jupiter was further evidence that the sun is at the center of our solar system and not the Earth. And he was able to explain the phenomenon that he saw by thinking of planets as things like the Earth with moons that go around them and rings around them, whereas nobody had ever seen those things before. The first time I saw the rings of Saturn, I was really excited. That was super cool.
Now, if you're looking carefully, as the image is wavering and shimmering, you can sort of make out a gap between the two rings. You just have to keep looking at it, but from time to time you'll see a gap there. And I think for me, that's an indication of how good the seeing is. If the atmosphere is really stable and the planet's up high, and you don't have a lot of moisture in the atmosphere, you can pick out that gap very easily. Right now, as I'm looking up, I see that there's a big cloud, big layer of haze that's moved in, and so it's just the contrast is really diminished because the moisture in the atmosphere is just reflecting a lot of light and just destroying the contrast. And in addition to just there's the seeing is just not very good here. Now, if we were to wait probably another hour, it'd be higher up in the sky, and so it'd be probably a little clearer unless the clouds move in. Let's see, I'm trying to see if we can't see any of its moons. Let me just hang on a second.
Now, usually you can see Titan, right?
Well, it just depends on, let's see, so yeah, in theory, Titan, yeah, we should be able to see Titan. So let's see if we can't, so let me just reposition this, move it up a little bit. I think I see something right about there, but let me move it up a little bit in the viewfinder or in the telescope. And let's see. It's drifting off. No, I don't see anything.
Yeah, it's probably lost in the atmospherics tonight.
Yeah.
Okay, well, we're probably going to be moving to maybe try a different object here in a second, but we have a telescope operator and an astrophysicist and a merit badge counselor. So if any of you scouts have any questions about the objects we're looking at or how we're looking at them or what they're made out of or anything like that, just type them in the chats and Carolyn will relay them to us.
Okay. All right. So now we're going to look at a double star. And this is one of my favorite double stars. It's called Albireo.
So after the invention of the telescope 400 years ago, people started discovering that stars often occur in doubles. And that is a new thing, and they had to figure it out. What is a double star? To the naked eye, it looks like just one star, but when you put a telescope on it, it turns out that there are two stars there. And in most cases, these are binary star systems. We thought they were just one star, but it's actually two stars that are orbiting around each other, and they can be different. And so I think we're going to try and go look at one of these double star systems and see if we can tell the difference between the two stars. Go ahead.
All right, so here, this is a double star. If you look at it, and now it's kind of hard to make out the color because I do have a filter in front of the camera, which is supposed to block out some light pollution, but it also shifts the color. But if you look carefully, and let me just put a magnifier on there. You can see one star is clearly blue, and the other star is sort of yellowish. And let me just show you where that is in the sky, because it was, I was really thrilled when I was able to find this on my own using something called star hopping. And so let me just stop this one and go to this one. Okay. So Albireo is in the constellation Cygnus. Can you see this star chart?
Yeah. I think some of our scouts saw Deneb tonight. If you want to start at that star.
Right. Okay. This is Deneb, and so then Deneb is the Northern Cross, or Cygnus, the swan. So this is the tail, the two wings, and this is the head. So Albireo is the star at the head of the swan, and these are some other pictures that were taken. You can just find these on Wikipedia on the internet. This one's interesting because it shows you where Deneb is in relationship to the summer triangle. So, but anyways, that's where we are, and so it's pretty easy to find. If you go out, you can see the summer triangle fairly quickly because there's three of the brightest stars in the sky, And then once you find Deneb, then you can quickly find the two arms or the cross, and then just go back, scoot down, and you'll find Alberio. So again, if you're looking at it through your naked eye, you only see one star. But if you're looking at it through a telescope, you can clearly see that there are two stars there. And I'm going to get it wrong, so I'll leave it to Tim to explain the difference in the colors.
Okay, well, let's we see one blue and one whitish to yellow and all those other pictures. What does that mean?
It's all about temperature of the outer layers of the star. The blue one is much hotter, probably 4-5 times hotter than the sun. And the other one is, well, actually, outer layer is probably cooler than the sun. It's a red giant star. Although it looks yellow, it's actually kind of a red giant. Each one of those two stars, in fact, is a double. So that's 4 stars you're looking at. But they're so close together, you can't separate them with any normal telescope. You have to use adaptive optics or an interferometer or something. They're very close together. And this pair is not gravitationally bound. They just happen to be close to each other in the star, but one of them's going one way and the other one's going the other way. And in 1,000 years or so, well, they'd be far apart and nobody will know they were a double unless they talk to some astronomers. Yeah, 1,000 years ago, they were right next to each other. Cool. But it's all about temperature. And they thought for a while there might actually be 5 stars, but the fifth one, I think, is a background variable star that comes and goes. But each one of those is definitely a double.
Hey, Tim, I was reading about Vega tonight because a lot of the scouts were able to see it straight overhead, and I think it's the brightest star in the northern sky. And
Sirius.
I was reading that was the first star that they were able to reliably measure the distance to.
No, that was not Vega. That was, I think it was a star in Pegasus. I can't remember which star it was, but it was the mathematician Wilhelm Bessel who did it back around the 1830, something like that. Vega was actually used as the standard to define the 0 point in the stellar magnitude scale, so that magnitude 0 would be Vega. But after they did that and wrote all their catalogs, astronomers discovered that Vega is the wrong brightness for its spectral class. And the reason is it's a rapid rotator that we see pole on, so the pole is brighter than it should be. So rather than rewrite the magnitudes for every star in every catalog, they just changed the magnitude of Vega from 0 to 0.03 or something like that. So Vega is not 0 in the Vega magnitude system like it's supposed to be, but that's the best we can do without rewriting everything.
Yeah, that's
So
one of
this is
those weird,
Vega.
like, what does this scale of numbers mean? It's just a way to measure how bright stars appear to us, right?
Yes, and in fact, that magnitude scale actually goes all the way back to Ptolemy and Almagest 150 BC. If it ain't broke, don't fix it. So Norman Pogson created a logarithmic scale, and he stuck with Ptolemy. So one magnitude is a factor, I think, of 2.5 in brightness. So stars that differ by one magnitude in brightness, that's 2.5 times. And of course, it multiplies. So if it's 2 magnitude is 2.5 times 2.5. It's kind of weird, but you know.
So what I was going to do is what I had read, Tim, is that Vega was one of the maybe early stars that they measured with parallax.
I'm sure they did. I don't remember when, but it wasn't first, but it was back there in the old days because it's bright, obvious.
Yeah. So what I was going to explain is, the Earth goes around the sun, and if you measure a star in the sky at one time of the year, and then 6 months later, you're looking at it, and that's enough of an angle that you can actually, with very precise telescopes and measurements, measure the shift. So like if the scouts, if you put your thumb out in front of your nose at arm's length and blink your right and left eyes, you will notice your thumb moving across the background of whatever room you're sitting in. So if you were to do that same thumb experiment, except do it on two sides of the sun when the Earth is different times of the year, and measure where Vega shifts to and from, you would then be able to have a triangle of angles that you could compute the distance. And that was one of the earliest ways that we were able to measure the distance to relatively nearby stars. And it's an experiment you can do with your own, thumb to see that it is an actual effect, that it shifts. But when things get really far away, that triangle gets so long and the angle so small that you need other methods to measure the difference.
Not only
So
that,
this
but if the star is too big, like Betelgeuse, is really hard to measure because nobody knows where the center of the star is. It's variable. It keeps changing its shape and changing its brightness. And the star varies in size as much as the parallax angle. So, distance, right.
Is that Vega we're looking at, Spencer?
Yeah, yes, that's Vega through a telescope. To be honest with you, other than double stars, I don't really like to look at stars through a telescope because you don't see much. You just see a blob like that. But that's also a very good example of sort of the effect of the atmosphere on the light coming from the star.
Yeah.
It's
So
even though
Spencer,
Vega is almost go ahead.
if we transported your telescope up into orbit, would the view change?
Sure, you would not have any of that atmospheric distortion.
Well, we could make your telescope Hubble too. We just have to launch you into orbit.
Hey, anytime I want to
ready?
go.
All right. Do you have any other objects you want to try? I know
Yeah,
that the Vega overhead, we might have a chance at
yes.
another object up there.
Yeah, so we'll try the Ring Nebula, of course. How did you guess?
Well, the Ring Nebula is not a star. It's a different kind of object. And we'll take advantage of having Tim. Spencer, while you try and see if you can find that object, Tim, why don't you tell us what process created this thing we're about to look at?
Well, it's the Ring Nebula, and you'll find out why when you see it. But a star like the sun, when it gets old and crotchety and temperamental, becomes thermally unstable and pulses in and out on a fairly regular basis. And each time it pulses out, when it collapses back in, it leaves a little bit of itself traveling away. So it builds up an expanding shell of gas around the star. And the Ring Nebula happens to be one that looks like a nice ring. We're actually looking down one end of what amounts to a cylindrical tube, but it's fairly nearby, so it's big and easy to see and has a nice round shape. They called Planetary Nebula because that shape in an old telescope is round like a planet and fuzzy like a nebula, so they call them Planetary Nebula. But once the Hubble Space Telescope started to look at them, they discovered, they have every kind of shape you can imagine. Some look like bugs and some look like splats. There's one called the Fried Egg Nebula, and there's another one called the Rectangular Nebula. Just every shape you can think of. But our sun will eventually become something that probably looks like the Ring Nebula in 5 billion years or so. So start making plans now.
Okay, so
Right.
the Ring Nebula is quite a bit fainter than the stars. So in order to get a picture of it, I'm going to have to take a 10-second exposure at really high gain or high magnification. So it'll be kind of noisy, but you should be able to see the ring. So I just took 10 seconds worth and it's downloading now. Okay, there it is. Now it's kind of distorted.
That looks kind of squishy.
Yeah, it's squishy. I've got a collimation problem here, but it's kind of squishy. Normally it'd be completely circular, but you can see it's. So yeah, somebody just squished it, but you can definitely see the donut shape, and you can also see some fringes. There's sort of reddish around the edge, and then bluish near the center.
Mhm.
And so, Tim, you want to talk about that for a second while you try and
Well,
magnify this?
the blue color, the colors in this case are not temperature. The blue color is characteristic emission from doubly ionized oxygen. And when astronomers in the 1800s first looked at something like the ring with a spectrometer, they did not recognize what that was. So they thought it was a new element, and they called it nebulium because it was in the nebula, and they didn't know what it was. And nobody would have thought about doubly ionized oxygen because that's crazy. How do you do that? But an astronomer at Mount Wilson Observatory did the calculations and realized that they were actually looking at doubly ionized oxygen, was the first to explain what nebulium really was. It wasn't another element, it was just good old oxygen. And the red color comes from hydrogen, and it's in the center of the nebula. You can't see it here. There is a very hot, almost white dwarf star, 50,000 kelvins or hotter, with a lot of ultraviolet radiation. And the ultraviolet is what excites the atoms and makes them glow. So they're basically fluorescing because they're being bombarded by ultraviolet. And so that's where the colors come from, as the electrons fall back into the atoms and then get kicked out again and fall back in. They give up the energy that makes that characteristic glow. And it's fairly nearby. I think it's only a few thousand light years away, and less than 10,000 years old, a few 3,000 years old, maybe something like that.
Okay. All right, that's about all I had, unless you want to, let's see, Mars is not up yet. I can swing over to, Antares is set below the, Antares is covered in clouds now. It's gotten really low.
Well, we've still got a half an hour. So what I'm going to do, I think, if you get another view, just speak up and we'll let you share. But what I'm going to do
Okay.
is start in on the last requirement, which is number 9, which is our discussion of careers. And then I'm going to leave 10 or 15 minutes at the end for discussion, questions, or if you have another view for us. I'd want to thank you so much, Spencer, for sharing that Ring Nebula with its weird colors and odd shape. Was a really interesting object tonight up near Vega.
Okay. All right. Sure. I'm going to poke around and see if I can't find something interesting.
Okay. All right.
So if you, I'll leave the screen share on unless you want the screen share.
You could stop sharing, but if you got something, just you know, you can start sharing again. That's fine.
Okay. All right. Okay.
Thanks, Spencer. All right. So the we're sort of winding down now. We're going to finish our last requirement, number 9, and give the scouts a chance to ask any questions. So we're having a good time tonight in terms of having extra time, which is good. You guys should be getting close to done on your worksheet. Obviously, you have some diagrams that you probably didn't get a chance to do tonight. You can mail me. You can finish it over the next few nights or over the next few weeks. But, you know, keep it nearby, finish it up and email it to me. So I've got a question out here from Alden on what do we do for number 8? So that's a good question. You're going to do 8B. And in the section where it says plan and participate in observing session, I want you to just put some notes down about what you saw either when you went out on your break or through Spencer's telescope. So put down, I saw Jupiter, I saw Saturn, I saw a double star, I saw the Ring Nebula. Those are the just kind of notes we want to know that you actually did an observing session. That's the requirement number 8. So you don't need to write whole story. It's just that you did an observing session and you learned something. That was the goal of that. And for number 9, the last one is career opportunities. Because you are young people and you're in school now, and you might think, well, a career in one of these fields related to astronomy might be of interest to me. What's involved? So I'll throw out a few ideas for you of the kind of careers that can be related to astronomy. We actually have an astrophysicist here, so I'm going to let him tell you about his journey and what it's been like for him. That's definitely a career related to astronomy. But an astrophysicist or an astronomer in an academic or perhaps even a setting at a company or for a government, astronomical researcher, that's a very traditional astronomical career. But as people point out to you, astronomy requires giant telescopes and computers and satellites. There's all kinds of engineering, from electrical engineering, mechanical engineering, optical engineering. All of those fields are related to astronomy in that to do astronomy, we need those engineers. And those are also typically, you know, math, science, and material related careers. Computers and digital processing are a huge part of astronomy these days. And so a career in astronomy might very well be a very computer-oriented career in building, maintaining, processing, programming the computers that deal with all the data that is gathered by these astounding instruments we have today. There are certainly others, you know, cameras, digital imaging technology is a huge field. It's very important to astronomy, but it's very important to earth science in general and many other, even if you get into Hollywood, some of the high-end digital stuff they have is not dissimilar from some of the stuff going on in astronomical digital photography. Obviously, satellites and telecom are, you have to know how things orbit things and be able to compute them. So you can write down any of these 3 that I've mentioned, but at this point, Tim has had a career of some interest, so I'm going to let him describe his journey and what he did and how he got to be what he is.
Well, I'm a physicist, got my bachelor's and master's degree in physics from Cal State LA, which has a good physics department and is a lot cheaper than Caltech. Maybe not as famous, but it's a lot cheaper. And I worked at the Jet Propulsion Laboratory for 28 years. And my career was more or less traditional in the sense that I went in straight through the scientific road to be a research assistant, technical staff, software engineer. They changed my job title so many times. I don't remember what I was. I worked there is about the easiest way to say it. But I did data science, data analysis. So I wrote a lot of software. I did a little observing, but not much. I really wasn't an observational astronomer. My brother was. He worked at Lowell Observatory and spent all of his career at the business end of a telescope late at night with an electrically heated suit when it's 5 degrees, you know, so he can survive the observing. But, you know, I got to work most of the time during the day at JPL. We made observations of the planets, and it looks like Spencer's got a globular cluster there.
Cool.
Right, that's the M13 Hercules Cluster. That's almost directly overhead.
Ah,
So
cool.
that's a cluster, a group of about 500,000 stars that are gravitationally bound.
That's right.
Okay. Yeah, I got it. I guess they're, now let me see if I get this right. So they were actually formed, they're kind of formed together, and then they're slowly drifting apart.
I don't think that cluster is drifting apart. Some of the smaller globular clusters are being broken up by the Milky Way's tides.
Okay.
M13 is too big for that.
Okay. All right.
So that's a pretty nice image. I mean, that's thousands and thousands and thousands of stars in an area of the sky about the size of, you know, one dot.
Mhm. As I recall, it's about 26,000 light years away. So the light you're seeing in that image took 26,000 years to get here from there. So it left 26,000 years ago and has been cruising through space all that time until it managed to fall into the tube of Spencer's telescope, which is fairly small. I guess it's an 8-inch. Is it a 10-inch?
9 1/4.
Oh, 9 1/4. I didn't know anybody had 9 1/4-inch telescope. So imagine some of the light from that cluster missed this telescope and just fell on the ground next to it and was wasted. Nobody saw it. So the lucky photons are the ones that made it into Spencer's telescope so you can see them. And so, yeah, and the cluster itself is about 13 billion years old. They're very young stars. They're not the first stars to form in the universe. People still looking for those, but they're very young stars. They formed a billion years or so after the universe began in the Big Bang. So they're very old. Most of the globular clusters around the Milky Way are.
If the Earth were in a star in that cluster, what would the night sky look like there?
Incredibly dazzling. If you draw a cube around the Earth with sides that are, say, 3 light years, so you have like 9 cubic light years, the only star in that cube would be the sun. There's no other stars in it because the nearest star is like 4 light years away. If you did the same thing at the core of a cluster like that, there'd be about 1,000 stars inside that cube. And so the night sky would not be dark the way we think of dark, because there'd be so many bright stars in it. It would be a lot more dazzling than the night sky we see. And of course, you wouldn't see a Milky Way because that's the plane of our galaxy. Your whole sky would be the same in every direction you look, just a whole bunch of stars, and there would be nothing like the Milky Way. But sky
So maybe
would not
there's
be all
another
that
civilization out there that doesn't know we're out here because they can't see through all the stars around them.
Well, look for a short story by Isaac Asimov called Nightfall, about the people on a planet with 2 suns, and night only comes once like every 100 years, and nobody's ever experienced it before. And when both suns set, they all go bananas. Like, what the heck? What's this? It's dark. I don't know what to do. It's pretty impressive. So if you like science fiction, just look for Nightfall, and that's always fun.
I remember that book. I read it when I was young. So anyway, thank you for that detour into thinking about what it's like in one of these bizarre globular clusters. And that.
Okay, let me just one slight detour here. Let me see if I can't. Jupiter is higher up in the sky now, and I just looked, and I could actually see one of its moons. So let's just. Nah. Well, let me just hang on. Let me just see if I can't pull up a magnifier here. Nope, it's still kind of yucky. Okay, I'm sorry. So thanks. Sorry for the.
Okay,
the
no,
detour.
thanks for sharing that globular cluster.
Okay.
That was really cool.
Good.
So let's see. We left off with Tim going to Cal State and working at JPL for a career related to astronomy.
Yeah. So I did the science route. I studied planetary atmospheres. I studied star formation, and I took a detour and did some geological remote sensing because I needed an astronomical scientist. And so I was the atmospheric guy, I should say. It's the atmosphere guy in a building full of geologists. We're all old and sunburned because they spend all their time out with rocks in the desert, chipping away out of a rock with little axes. But as Greg said, there's so many ways to get into astronomy. Just about every career you can think of is one you can reroute towards astronomy. And of course, you can always just be an amateur astronomer and a professional and whatever else you want to do, and just go out and do what Greg does, do what, in fact, you're a computer guy, aren't you, Greg? So, yeah, so you want to know about computers, ask him, not me. He's the computer guy. But one of the things I was thinking about is the big telescopes, the really extremely large telescopes they're making now. And in fact, the biggest one is the extremely large telescope. It's a 39-meter aperture telescope that's under construction in South America now. That's 130 feet across. And its moving weight is 5,500 tons. And you have to move it, as one friend of mine said, with the precision of fine Swiss watch. So 1 arc second of angle is the same as a dime seen from 2.5 miles away. So imagine 2 dimes right next to each other, 2.5 miles away, just touching right next to each other. You have to point that 130 foot across 5,500 ton telescope at one of those dimes, and you have to know which one you're pointing at, the one on the right or the one on the left. And you have to be able to move it to the other one precisely with 5,500 tons. So that's not an easy thing to do. It takes some serious design, construction. So it's the architecture, it's the design, mechanical engineering, the construction engineering, the electrical engineering that goes into it. And of course, some of the most powerful computers in the world are attached to these big telescopes. So they have plenty of computer scientists. They have optical design people to design the optical paths. As Greg said, instrument designers, which has a lot to do with what we call applied physics, which is old jargon. They still call it that. Solid state physics, the way you design a detector to be sensitive to certain wavelengths, whatever it is you want to do. But even ordinary electricians, just like the guys who work on your house, well, they got a lot of electricity running around in those places, and somebody's got to lay wires and fix all that stuff. And they're not really electrical engineers, they're technologists. And people familiar with telescope operations, it's a form of technology. Little telescopes are fairly easy to operate, but those big things, you can't just go push buttons and move them around. You got to be careful what you do with something that weighs 5,500 tons, because if you hit the wrong thing with it, the immovable force and object and all that stuff, it's pretty bad. And so there are lots of ways through technology, science, engineering to get into astronomy as a profession or as an amateur astronomer. And do remember that the lead guitarist for Queen, Brian May,
which was a famous band.
Oh yeah, they used to make music. You kids are too young. He was actually majoring in astrophysics when the band became famous, and he quit and ran off and got rich and famous. Then he came back and finished. So he has a PhD in astrophysics, studying zodiacal light and dust in the solar system. And now he does a lot of teaching. He's an astronomy professor after being a famous rock guitarist. So you can even lead a rock band and wind up in astrophysics. It's possible. It's been done by at least one guy.
As I recall, he was like a pretty hardcore student when his band hit, and like he diverted into being a superstar for decades, and then he came back. It's interesting.
Right up.
Engineer, research, computers, these are all fields of engineering and technology that are directly needed and available as related to astronomy and astronomical related careers. I think one of the questions that the last question the scouts kind of have to think about is, what would be of interest and what could I do to prepare for such a career? Tim, if you had any advice for someone that was interested in one of these technology or research stacks and they were getting ready to go to high school or already in high school, what's the path?
Well, first and foremost, all of them without exception, require a good knowledge of mathematics. So whatever you're going to do, you have to at least go through standard calculus. And then if you're going to go into physics like I did, you go beyond that. But they all require mathematics. So if you want to go the scientific route, you're going to need physics, math, a little chemistry helps, but yeah, okay. Don't tell the chemist I said you don't really need chemistry, but it's physics and math are certainly through high school. That's what you want to concentrate on. And believe it or not, the other thing I stress, because it's something that I did, so naturally I think anything I did is brilliant and everybody else should do it, is language skills. I've learned Russian and French and a few other languages on and off, and I do a lot of talking. Sometimes I talk too much, but I do a lot of public speaking. And being able to explain to someone what you're actually doing is a pretty valuable talent. Because I know people at JPL who are still there who are really, really smart. They're great scientists, but they cannot tell you what they're doing. You have to sit there and prod them and question them, and eventually you'll get it out of them. Oh, that's what you're doing, but they just don't have the language skills to explain it. It really helps to be able to do that. And it's, if you get a job someplace and you want to stay there, that's a really good thing to be able to do. So basically it's that, math, physics. If you know you want to do astronomy, then there are degree programs in astronomy. You just do that, and it's an observational science. If you're not altogether sure what you want to do, because there's lots of things to do, I always suggest that you do what I did, because again, I did it, so it's got to be brilliant, right? Is that physics is the most fundamental of all the physical sciences. It is the fundamental science of matter and energy. And if you get fancy, space and time, but you don't need to worry about them usually, matter and energy. And so if you have a background in physics, you can go into geology, geophysics, chemistry, weather, you can just all kinds of things. All those physical sciences are basically physics. So if you don't know what you want to do, you can just study physics and then work your way into something else later on, and it'll do just fine. If you know you want to do astronomy, or you know you want to do meteorology or whatever it is, well, then go into that program and do it. But if you're not sure, whatever it is you choose to do, you'll know you will be fundamentally prepared if you have a good background in physics. And that's particularly true of engineering. And now, because the fields are so similar, there is a field called engineering physics, which combines physics and engineering to give you a little of both, because physicists are not usually as practical as engineers are. Basically, physicists make up the rules and then engineers play the game.
Or try to, or approximation thereof, right?
Yeah.
All right. Well, I think we had about 10 scouts in our class tonight, and I want to give them a chance.
I think Spencer was trying to say something.
Yeah.
Oh, go ahead, Spencer.
Let me just share one more. Let me share one more image, and I realize why things are so crappy. The Azusa, because I couldn't figure out what was going on, but this is the Dumbbell Nebula shapes.
Are you sharing, Spencer?
He is now.
Oh, there we go. Yeah, it's kind of faint, but there it is.
Yeah, it's called the Dumbbell Nebula because it's got a couple of globs attached with a little stick, and it looks like one of those dumbbell things if you get a really good image of it. I don't
sorry,
remember how
what was
far
I?
away it is.
I lost the internet partway there, so I couldn't. So You guys are still able to see the image now?
Yeah.
Yeah, we can hear you
Okay,
now too.
Okay, good. Yeah, so yeah, so this is the Dumbbell Nebula. So it's sort of again, you can see traces of a hint of reddish around the edges, right here, and then the nebula itself is sort of like a dumbbell or an apple core.
So this is another one of those things that we were talking about that kind of blew up and spread gas and ions and stuff around. Probably a star exploded or something.
Yeah.
It's another planetary nebula, just like the ring, only, as you can see, much different shape.
Yeah. Okay, so that's all I'm gonna be showing tonight because it's starting to get kind of smoky up here. I think the wind shifted and we're getting a lot of smoke from that fire in Azusa now.
Oh, wow. Well, be safe. Thank you for sharing,
Well,
Spencer. It was really nice.
Okay.
All right. So as we got 10 minutes before we're officially done, and we've talked about the careers in astronomy and how you would prepare for a specific one or maybe a category of a career if you don't know for sure. I hope you guys have enough notes to complete your packet. If you wanted to ask Tim a question about the careers or about, black holes or distant galaxies, here's your chance to talk to someone that has the correct answers. I just have the hobbyist. I read a lot and I know some of the answers, but I didn't spend my whole career studying it. So I will hang out here for 10 minutes more. If you have any questions about finishing your packet, like what about this number? I'm happy to answer further questions. You can always email me directly. Yeah, if you're on mute, there's few enough. If one of you wants to come off mute and ask a question, just go right ahead. We got a quieter group tonight. Maybe they're so busy taking notes that they don't have any questions.
Got it all figured out.
So I'll give a few other astronomy related activities. They're all closed right now, of course, because most of the public events and astronomy sites are shut down right now for COVID. But hopefully in the next 6 months or a year, this will pass and we'll be able to, go scouting again and go camping again and see the night sky. I think Tim is on the historical society that runs Mount Wilson Observatory. And he, I think, used to or still does tours for the public up there on Sundays during the summer, if we were open, right?
Yeah, if we were open. We're not now, but I would be doing them. I've only been doing it. I'm on my 40th year now.
Only 40 years?
Yeah.
Well, what I was going to tell the scouts is next summer, if we're open and things are safe again, we have this amazing historical observatory right in our backyard. It's open to the public on the weekends, and you can just go up there and either walk around the grounds and go into the viewing galleries, or I think on Saturday and Sundays they have tours you can sign up for at the Cosmic Cafe. When I came out here to California in 1984, the first place that I went was Mount Wilson. I didn't go to Disneyland, I didn't go to the tar pits, and I didn't go to Grauman's Chinese Theater. I grew up looking in books at the pictures of the 100-inch, and that was the thing I wanted to see, the telescope that Hubble used to gather the evidence for the expansion of the universe. And it was really, really cool. It's a very fun trip and a nice hike up at Mount Wilson. Here in LA, down in Monterey Park, we're not open right now, of course, because of COVID. But when we're reopen, I'll send out some invitations for those of you that complete the badge. And you can meet us over at Garvey Ranch Observatory. And we can meet in person. And assuming it's all safe and everything, we can go up in the dome and have some telescopes on the lawn and do some actual observing instead of this remote stuff. But in the meantime, you can earn the badge, send me your packet, I'm still grading papers from the July 22nd class, but I've just about got all the blue cards out for that, so I'm ready for a new wave.
Yeah, it's good for you.
Yeah. Yeah, so
Mr.
there's a couple
Thompson.
questions floating in about the packets. If you fill out your packet with pen and paper, just scan it, or you can actually mail the actual workbook to me if you need to. If you want to fill it out as a PDF, the thing I sent you is a fillable PDF, so you can just type your answers in and save the thing.
Word file.
Oh, did I send the Word file?
Yeah, so I
Yeah.
included it in the chat. Yeah, all of them actually.
Oh, okay. So yeah, Carolyn's put a link in the chat to the PDF version of the astronomy workbook. And you could use that to fill it out too. If you send me your workbook and it's all done, I'm going to send you back a digital image of your blue card all filled out. If you want your actual blue card, send me an email with the address and I'll drop it in the mail to you, so you'll have not just a print of your blue card, but the actual blue card. As you know, if you're going to make it to Eagle Scout, you need to keep track of all those cards so you can prove you did all the requirements, and keep all that stuff in a binder. I've known a few scouts, they earned all the badges, they went to all the camps, they did all the requirements, and they get up to Eagle Scout and they can't prove it, you know. So save your evidence for that that time when you're going to make Eagle Scout. It's a big deal.
Yeah.
And so I think if there's no further questions, we're about ready to sign off. You got about 5 more minutes if anyone has any questions.
Mr. Thompson, I have one question.
Go ahead.
This is Sai Samantham.
Hi, Sai.
So for the merit badge workbook, so for the requirements where it says to like draw out the moon and all the craters and to draw out the moon phases, is it okay if I do that on a separate sheet of paper and just attach that in my PDF? Because I'm doing the fillable PDF one and I can't like hand draw it.
Yep. No, that's perfect. A number of scouts do that.
Okay.
You can fill them out on a separate piece of paper and just shoot a picture with a phone or whatever, and then attach those photos in the same email as your PDF. I'll just check them and I'll fill out your blue card and send it to you. That's great.
Okay.
Thanks.
Okay, thank you.
Yeah, as I said, right now the moon is not, at least right now, it's good for astronomy right now because it's not in the sky. It's not messing up our view of the sky. Your moon drawings, if you want to do them by getting up early in the morning, that'll work. You can check that Sky and Telescope website or just Google moonrise and moonset, and you can see what times the moon's going to be up. You need to see the moon 4 nights in a row or 4 mornings in a row if you get up early enough. And yeah, it's in the paper too. Yeah. Yeah, but if you run any trouble with, I think probably we're running around 60 to 80% of the scouts completing the badge. And the thing that seems to hold them up the most is just doing the planning to go out and look at the Big Dipper and the moon to make your drawings. You know, if we were at summer camp, we'd just go out and do it together and then we'd be done with it. But here we are remote. So if you run into any questions or like, I can't find the Big Dipper, you know, I am your counselor. Just reach out to me in email and I'll try to provide whatever help I can. And we'll get those requirements complete. So thanks a lot. Okay, guys. Carolyn, you want to, oh yeah, so there's a great picture. Thank you, Carolyn. So this is what we're looking for here. Yeah, so go down and show the cup of the Big Dipper. There's the cup of the, no, that's the handle, that's the cup. Now the outer 2 stars are your pointer to a really bright star. That's Polaris. So the Big Dipper sketch is to draw the Big Dipper as it moves around the pole star there. And then it'll move a bit each night, depending on what time you're out. You can use your star wheel, star map, or a cell phone to help you find it if you need to. But you are gonna need kind of a dark sky towards the north. So if your northern horizon is blocked by trees or apartment buildings or something, you'll have to figure out some place you can go at night that's safe and that you can observe the sky to do your Big Dipper drawings. It's 2 drawings. I think like an hour or two apart, so you can show the motion of it moving around.
They don't even see these stars here, not in Los Angeles.
Yeah, you can actually see the little
See
difference.
these, see that one,
Yeah.
Yeah, this picture here is from the night of the Perseids just 10 days ago.
The day before the fire started.
The day before the fire started. So this is at our Garvey, no, it's at our Lockwood Valley dark sky site. And this is the sky we saw the meteors streaking across. And you can't see that many stars in Los Angeles because of the light pollution. So that's a beautiful sight to view at. All right. Well, I think I've tried to do as much as I could do and make it fun for you. Thanks for signing up and joining. Thank you, Tim, and thank you, Spencer, for joining in tonight to help us complete the badge for these scouts. And I'll look forward to receiving your worksheets, and that will hear me next. If you complete the badge, I'm going to keep you on a mailing list so that we can have a scout night at one of our observing sites, maybe probably not this fall, but maybe next year. Oh, here's a picture of is this Sagittarius?
Yeah.
Yeah.
Jupiter,
Oh, there we go.
Saturn.
Oh, yeah. So if you guys saw the Jupiter and Saturn tonight, that's where the Milky Way should have been had you been able to see it in LA, which you can't. Those
And this glow is Los Angeles.
Yeah.
those dark lanes in the center of the Milky Way galaxy, those aren't actually voids in the Milky Way galaxy. Those are dust clouds occluding the view of the stars behind them. So it looks kind of like dark lanes or gaps in the Milky Way, but what it is in reality is stuff in the way preventing us from seeing the rest of the galaxy on the other side, if I'm describing that correctly.
Yeah.
All right. All right, everyone. I'm going to sign off here and say thank you for joining. You have my contact information as your counselor. Good luck on the workbooks. And thanks for joining us for the Astronomy Merit Badge tonight. I had a lot of fun.
Thank you.
Good night.
Thank you. Good night.
Thank you.